Hey guys, so we're going to go ahead and continue our conversation about Unit 4 today. We have so far talked about chemical and physical processes. We have talked about several different ways to represent those chemical and physical processes, whether that's complete molecular equations, net ionic equations, or even particulate diagrams. And then we've talked about how we can apply that knowledge using stoichiometry and how we can use stoichiometry and a balanced chemical equation to tell us how much product we can produce, what our percent yield is. If we have something in excess, if we have a limiting reactant, we can determine volume, we can determine mass, we can determine volume of a solution. So we have lots and lots of tools at our disposal. So now we're going to jump in and we're going to take a particular type of reaction, and that is a titration. So let's go ahead and share our PowerPoint here. Maybe. There we go. All right, so here is our PowerPoint. We're going to be talking specifically about titrations today. We'll come back to the idea of titration curves in Unit 8 when we talk about acid-base reactions in great detail. So first, let's talk about what a titration is. So a titration is really just a volumetric analysis. It's a way for us to use the volume of a known concentration solution and the volume of an unknown concentration solution to determine the concentration of that unknown. So just like we have used spectroscopy to determine the concentration of an unknown, this is just another tool at our disposal. So in a titration, we are using volume and concentration of one substance that is well known to determine the concentration of another substance. We do need to know what both of the reactants are so that we can determine what their coefficients are going to be in a balanced chemical equation, but we don't know the concentration of the second one. So usually in a titration, we're relying on a color change to tell us when we have reached the equivalence point. Very often that color change comes when the indicator changes color. There are also times when the components of the solution themselves, because of the chemical change, actually change color. So we can have a titration with an indicator, or we can have a titration without an indicator. Okay, sorry, let's back up and talk a little bit about the equipment in a titration. So when we do a titration, we need to know the volume of the standard or the known solution very, very accurately. And we also need to know the volume of the unknown solution very accurately. And so we will usually use a volumetric pipette in order to measure out the volume of the unknown, because that gives us a very exact amount. So the volumetric pipette, very much like the volumetric flask, measures only one specific volume, but we do have different volumetric pipettes from 1 milliliter all the way up to a 50 milliliter volumetric pipette. And those are 4 or 5 significant figures of precision. So a very precise way to measure the volume of the unknown. Then we want to be able to measure the volume of the known solution just as accurately. And so we're going to use the burette, and the burette has graduations on it. It's graduated in tenths, which allows us to read it to the hundredths place so that we can determine very accurately, very precisely, the volume of solution of the known concentration that we're adding to the solution of the unknown concentration, and trying to see this color change at the equivalence point. So let's go ahead and talk about this idea of an equivalence point. So an equivalence point is the point where the two solutions that are being used in our titration are present in stoichiometrically equivalent amounts. Not necessarily equal numbers of moles, not necessarily equimolar, but stoichiometrically equal. So if you have a 2-to-1 ratio in your balanced chemical equation, you would have that same 2-to-1 ratio in your solutions. So that's the equivalence point. There's a small difference between an equivalence point and an endpoint. The endpoint is when our indicator actually changes color, or when we are physically able to perceive the color change. We want the endpoint and the equivalence point to be as close together as is possible. And so that means that when we choose our indicator, we're going to choose the appropriate indicator, the one that is going to change color as close to that equivalence point as possible. And so different titrations, particularly acid-base titrations, which again we use indicators for, they reach that equivalence point at different pHs. And so we want to choose the indicator that will change color at the appropriate pH. And so we would look at a table like this one that tells us where that color change is going to occur so that we can choose the appropriate indicator for our reaction. And we'll come back to this idea of choosing the appropriate indicator when we talk about acid-base reactions again in Unit 8. Okay, so let's go ahead and do some practice. So I'm going to pause here for a second. Okay, so we're going to take a look at this particular exercise. So in this titration, this is an acid-base titration. We're titrating hydrochloric acid with aqueous ammonia. Actually, we're titrating aqueous ammonia with hydrochloric acid, sorry. So we know the molarity of the hydrochloric acid. It's 0.1032 molar. We use our burette to determine the volume of the hydrochloric acid that we're using, and we get a volume of 29.28 milliliters. And we have used our volumetric pipette to measure out 25 milliliters of aqueous ammonia. And this is asking us to calculate the molarity of the ammonia. Well, we know the molarity equals moles over volume in liters. Okay, so we know the volume, we want the molarity. That means we need to find the number of moles. So what I'm trying to find, I'm identifying my unknown. I need moles of ammonia. Okay, so I'm going to start with what I know. I know that I have 29.28 milliliters of hydrochloric acid, and its concentration is 0.132 molar. So I'm going to start with 29.28 milliliters of hydrochloric acid. Now, I'm not going to convert this to liters. I'm going to leave this in milliliters. That means that my answer is going to come out in what we call millimoles. So this is the beauty of the metric system, is that I can just carry that prefix through. If this bothers you, feel free to change it to liters. I'll show you at the end of the problem why I choose not to do that. Okay, so I have 29.28 milliliters of hydrochloric acid, and I know that I have 0.1032 moles of hydrochloric acid in every 1 liter of hydrochloric acid. And I also know, I need a balanced chemical equation. I started a stoichiometry problem without one. That was a bad idea. So I have hydrochloric acid, and I have ammonia. And these two things are going to come together to give me ammonium chloride. Okay, so we went from having an acid and a base to having a neutral salt. In this case, we're not seeing the water. I promise you it's there, but we have neutralized our acid and our base. Okay, so now I know that this is completely balanced. So this is a 1-to-1 ratio. So I have 1 mole of hydrochloric acid is 1 mole of ammonia. Okay, and so when I work this problem out, 29.28 times 0.1032, I get that I have 3.02. Now I'm holding on to that prefix from milliliter. I have 3.02 millimoles of ammonia. Okay, because my other moles have canceled out, liters canceled with liters, and left me with just that prefix of milli. So I have this many millimoles of ammonia. But I want molarity. So now if I take my 3.02 millimoles of ammonia and I put it over 25.00 milliliters of ammonia solution, then I get 0.121 millimoles over milliliters is the same thing as moles over liters, which gives me molar ammonia. Okay, Because all of my units were in milliliters, I didn't need to convert away from milliliters because I was going to wind up dividing by milliliters at the end. It would be totally fine to call this 0.02928 liters, but then I would need to divide by 0.025 liters. And every time you do a conversion, you give yourself an opportunity to make a mistake, and you have to do an extra step. Speed is of the essence on the AP Chem exam, so this is why I don't convert. If you're more comfortable converting, that is totally fine. You do you. Okay, so we have our concentration of ammonia here. All right. Let's do another practice problem. Okay, we now have 10 milliliters of hydrogen peroxide that are being titrated with 35.78 milliliters of 0.025 molar potassium permanganate. Now this one is a redox reaction and it's kind of a pain to balance, so I've gone ahead and balanced it in advance. We know that we have 5 moles of hydrogen peroxide for every 2 moles of potassium permanganate, along with 6 moles of hydrogen ions. This is being done in an acidic solution. Yields 5 moles of oxygen, 2 moles of the manganese 2 ion, and 8 moles of water. So it's asking me for the molarity of the hydrogen peroxide. So again, we want to remember that molarity, keep doing that, equals moles over volume in liters. Well, I have volume, but I don't know moles. So the thing I'm looking to find, my unknown, is moles of hydrogen peroxide. I have a balanced chemical equation right here, so I can go ahead and get started with what I know. So my known is 35.78 milliliters of the 0.025 molar potassium permanganate. So I'm going to go ahead and convert this time just so you guys can see what that looks like. We have 0.03578 liters of potassium permanganate. And we know that for every 1 liter of potassium permanganate solution, we have 0.025 moles of potassium permanganate. And we know that for every 2 moles of potassium permanganate, we have 5 moles of hydrogen peroxide. And so we can work this whole problem out and we get 0.002236 moles of hydrogen peroxide. Okay, so that's a lot of zeros. This is why I usually don't convert to liters, but again, totally okay. So we have the 0.03578 liters times the 0.025 times 5 divided by 2 gives us 0.00236 moles of hydrogen peroxide. And in order to get to molarity, I am again going to take my moles, 0.002236 moles of hydrogen peroxide, and I'm going to divide it by my volume. This time it has to be in liters because I used liters here, 0.0100 liters of hydrogen peroxide. And we get a molarity of 0.2236 molar hydrogen peroxide. Now, it also asks me for percent concentration of hydrogen peroxide, and percent concentration is always going to be in terms of grams of solute per 100 grams of solution. So I'm going to change my molar to moles of H2O2 per 1 liter of hydrogen peroxide. And if I want grams per 100 grams or grams over grams times 100, Then I need to change my moles of hydrogen peroxide to grams of hydrogen peroxide. And that would be 34.015 grams of hydrogen peroxide for every 1 mole of hydrogen peroxide. And I know that 1 liter of water is 1,000 grams of water, because there's 1 gram per milliliter. And so when I work all of that out and multiply it by 100, I get 0.76% hydrogen peroxide. So this would be some pretty old hydrogen peroxide if you're talking about the bottle of hydrogen peroxide under the kitchen counter or bathroom counter, because that should be approximately 3%. But we know that this decomposition reaction happens over time, and so it does decrease its concentration over time. Okay, again, don't have to know percent concentration for AP, just a good practical example of converting of stoichiometry. Okay, one last practice problem. And this one is a little bit simpler. We're back to an acid-base reaction. So like any stoichiometry problem, we're going to start by writing our balanced chemical equation, which I haven't given to you this time. So I have acetic acid, HC2H3O2, and I'm going to combine it with barium hydroxide. Both of these are aqueous, although the barium hydroxide is just barely. And they're going to combine. I'm going to have barium acetate, that's my salt, BaC2H3O2. But since the acetate ion only has a -1 charge, I have to put a 2 here. I know that this is going to make water because this is an acid-base reaction. I can see that I need 2 acetate ions, so I'm going to go ahead and put the 2 here. That gives me 2 hydrogens and 2 hydroxides, which is going to give me 2 water. Okay, so we now have our balanced chemical equation. I'm being asked to find how much barium hydroxide is required to reach the equivalence point. So this time I have a different unknown. I'm not looking for moles. The unknown that I'm looking for is the volume of barium hydroxide. So I'm going to start with what I know, identify the unknown and the given. Here's my given, 25 milliliters of 0.105 molar acetic acid. So 25 milliliters, 25.00 milliliters of acetic acid. And I know that in every 1 liter of acetic acid, I'm back to staying with milliliters here, by the way, there's 0.105 moles of acetic acid. And I also know that for every 2 moles of acetic acid, there's going to be 1 mole of barium hydroxide. And I know the molarity of the barium hydroxide. So now I'm going to use the molarity as my conversion factor here at the end. So I'm going to say 0.985 moles of barium hydroxide for every 1 liter of barium hydroxide. So now I have 25 milliliters times 0.105 times 1 times 1 divided by 2 times 0.985, okay? And if we look at our units here, moles, whoopsie, moles cancel out, moles of barium hydroxide cancel out, and then acetic acid cancels out here, liters cancel out there, and my answer is going to be left in milliliters. And so when we work through all of that math, we get 13.3 milliliters of barium hydroxide. Pretty simple and straightforward, just a different application of stoichiometry. and it's asking you to think through the process that you would do in the lab. So as always, if you have any questions, please let me know, and I will look forward to seeing you next time.